Hello everybody, myself Sai Praveen Kadiyala. Today we are will be discussing about this work of ours, program behavior analysis and clustering using performance counters. This is my team, myself Sai Praveen, uh, Karthik, a student intern who worked with us, and Truong Utram is my colleague at I Square R. So yeah. So to begin with, briefly discuss about the problem we are trying to address in this particular work. It is well evident that there are two major ways of analyzing a program, a given program, the static analysis and the dynamic analysis. In the static analysis, the emphasis is laid on observing the binary of the program, so the patterns of the code and so the analysis of various artifacts, memory artifacts and things like that. On the other hand, dynamic analysis involves detonation of the program and often various features like API call, system call, instruction traces, memory writes. So like this, various features are observed which occur mostly during the runtime of the program, and dynamic analysis is effective across many other programs where static analysis is not effective, especially for advanced malware. So what we are trying to do here is we use performance counters as a feature for characterization of the programs. Recently, researchers have focused using usage of these features because most of the modern day processors are coming inbuilt with this particular, you know, PMU, the counters which can measure the particular microarchitectural events, the low level features. Current work, most of it is whatever available based on the performance counters. So they focus on obtaining the performance counters for the entire program, or for they try to estimate the average of performance counter values over a particular window, and they keep moving that window. So that is called as moving window average, estimated moving window average. So these are the two major things, uh, major directions in which the performance counter based work is going. So however, we felt that that particular representation may not, that particular idea may not be able to characterize the behavior of the program accurately. Suppose the time series behavior is not taken uh, directly into account. Of course there are some people who are averaging things out, but what if, so we consider at every specific instant of time, so the behavior of the program. So that is one of the main focus in our work. So as discussed, so it can be counted in two ways. We start extracting at the beginning of the program and obtain collect at the end of the program, or over a time period. So why these things are insufficient? Because uh, deviations during the course of the execution of the normal program, so that can be identified when we go to the fine grain understanding of the dynamic behavior of the programs. So what we mean by fine grain is like the time series, we are going to sample based on the time. So there are other ways also, like based on the number of instructions and things like that, but here we restrict ourselves to the time instance. Okay. So during its normal operation, so how the time series behavior is there, and then during a given 0 day analysis, so how the behavior is occurring. So these things are important to ponder over. So the research question, like so why we chose this performance counters, because often this system calls and the API calls, the other things what people use for dynamic analysis, mostly are of high level in nature. So so these and the methodologies built using these features also, they deal with the high level data. So, and we with an understanding that low level data is relatively tough to be tampered. So it's not that it's impossible, but it's relatively tough. So that's why the microarchitectural events and other data, so which are happening at a processor level, so these things are difficult to be tampered, and hence we focus on using this performance counters as an alternate feature to the other existing system calls and API calls like that. So now another challenge what we face is when we change from processor to processor, or system or environment to environment. So these definitions of microarchitectural events, and they change drastically. So do the tools that are available for extracting those performance counter data. So they keep changing. So it's important that we develop our own tool for efficiently extracting the performance counter data for a given environment. So in order to overcome these particular drawbacks or challenges existing, so what we try to do is, like, we develop our own tool for extracting the performance counter data for the environment what we have chosen. So that is a perf extract tool. And then the perf extract tool just not only collects the performance counter data, but also it collects in a proper time series fashion, and it coordinates also how to detonate the benign program. So we'll be elaborating that in the few further slides. Yes, so this is what is the main important question, that okay, we are extracting the time series performance counter data. So what is the purpose of it? So the purpose is that we explore a low level performance counter based clustering of benign programs based on the performance counter data during their runtime. So we try to cluster a set of benign programs. So are these time series data giving a meaningful representation of the programs? If so, at what level? Is it at a domain level, or it is at a fine grain each executable at that particular level? What particular granularity? So that's what we are going to discuss. So so to the best of our knowledge, this particular time series performance counter data, and then based on the clustering of the programs, is not yet explored. So that is what we are trying to do in this particular work. So this is a brief overview of the our approach. uh, we first of all, we effectively cluster the behavior of the program. So that is the main thing, so that it can distinguish itself from the other programs. Now, at what level? Is it at a domain level, or it is an individual program level? What is efficient, that we analyze. So in order to carry out this experiment, and then we also want to identify any possible deviations. Suppose a program is installed already and then it's running, but suppose it's compromised because of an external attack or things like that, any update. So how its behavior is different from the uncompromised version? Can our method detect that? So that also we are going to do. uh, so we'll be explaining the data set chosen in further slides. So these are basically various domains we have chosen: text editor, web browser, image viewer, and audio player, and some of the programs for each of these domains. So this is a high level block diagram. Like we have the programs, we have developed a perfect extract tool which extracts the time series data, and then this particular data is fed into the ML clustering, and then it clusters into various different programs. So we have got a data extraction module, so where the tool extracts based on the programs that are running, and then based on the extracted data we see how much, which features, like which microarchitectural events are effective in modeling. There are some particular microarchitectural events which are just constant throughout the program, or they have they don't convey program specific, any information. So like something like date and then all those things, priority based. So so we discard them, and then so this is what is the key feature identification. So the time series data for those particular key features are fed into the ML model, and then we see the cluster. So our solution framework consists of two components. So first part is the data collection, which we use the tool, and then we do the program clustering. So our tool works on a virtual environment. We are doing it so that currently we are doing it for the benign programs. In future, we try to extrapolate for the malware, and then we can refresh after each and every program analysis is done. So that is one of the main objective. So this perfect struct tool, it starts extracting, and the tool is triggered, and after the tool is triggered we detonate the program, so that the behavior of the program right from its detonation is captured. So we see the redundant values in the first interval, and then we remove that. And then we chose the clustering because into different groups, because so clustering, it doesn't need a labeled data set, so which is in practical scenarios that is true, because it's always we don't get a labeled data set. So we use a k-means clustering algorithm to classify the programs based on the time series data. And then initial seeding, we assume that the programs are behaving in a normal way, so based on that we seed the clusters. And then when the testing phase, whenever a new program is coming, so we identify the closeness or the proximity of the program to any one of these clusters. And if a new sample um, uh, is not able to identify any proximity to one of the clusters within the defined threshold, so then it itself will form a new cluster that shows that it is aloof from the existing behaviors. So this can be possible either because it's newly installed and then first time it started detonated first time it's detonated, or it can be that the program has changed its behavior because of some compromise or an attack. So this is a description of the data set earlier mentioned. So we have got we chose 18 programs to analyze. These are all the benign standard programs. In the four domains, these programs span across four domains: text editors, web browsers, image viewers, audio players. And then in order to make it more general or practical, so what we try to do is, like, each of these programs, so we have given 20 different inputs like arguments, so that so we characterize the behavior of this particular executables across various arguments, so that the modeling will be much robust. And then so each of these input arguments also, so we did this in 10 different runs, because there is a minor lack of determinism in the performance counter values from one run to another run. So in order to overcome this minor non-determinism, so we uh, uh, collected the data over 10 different runs, and then used all this data for our further clustering of algorithms. So overall we get 3600 samples, 18 programs, 20 different inputs, and then 10 different runs. So this is the data set what I have considered: text editor, Atom, GVim, Notepad, Notepad++, Sublime Text. So 5 programs from each of the first 3 domains: web browsers, image viewers, and then for each of these programs 20 input different input arguments, 20 samples, and then 10 different runs, that is also there. And the audio player we chose 3 programs: Clementine, Foobar, and VLC. And then the input arguments are also from the standard databases. So this is the evaluation of our methodology. So this is some of the test cases which we have shown. Like these are the seeding clusters where the normal behavior is observed, and then the normal behavior is expected in the seeding time. So we chose 3 clusters as a seeding clusters, and then we tested with a 4th one. So like that we performed a lot of combinations, and then we this is the result, whether this particular 4th executable is different from the existing 3 clusters. So whether it is detected as a different one, so it made its own cluster. So that's what it means by detected. So it's different from all these 3. So like that there are various cases. So it's important to observe that some of the cases it did not, like we see number 6 and then number 9. So GVim, Vivaldi, Clementine, so Brave is not detected as a separate cluster. So what it means is that so the behavior of this particular program with respect to the performance counters as modeled by performance counters is close to one of these 3, or maybe more than one. So like that we performed the clustering, and then we achieved an F1 score of 98.72 for our approach. It's decent enough. So there are some other results which substantiate why we are using performance counters, whether they are effective or not. So here we see the time series representation over 30 seconds, 30 time intervals. We have collected the handle count and page file bytes for various programs. We can see here GVim and Notepad, these are the text editors. So they are close, and then Brave and Google Chrome, so they are at another particular level. So there's a quite difference at a domain level also. And then we see another performance counter. Still there we can see that there is a clear-cut distinction, but here we can understand that the distinguishing factors at the executable level granularity. It's not at the domain level, but at executable level the distinguishing factor is much more. And these are the box plots of the inter-cluster and intra-cluster distances for at a domain level as well as at executable level. So we have 18 executables, 4 different domains. So this is the intra-cluster, the top 2, and then the inter-cluster. We can understand that at a domain level, if we can carefully see, there are certain clashes, like the inter-cluster is less than the intra-cluster for some of the clusters apparently. So but when we go into the executable level, so these things are much more differentiable. And then these are the TSNE visualizations of various cases. So we can see that there is a clear-cut separation between the executable level programs, like in this case Atom, Brave, Wildbit, and Clementine. So this is one from each of these domains. So we can see that clear-cut distinction is there for, of course, various other cases also. However, we can see that if we consider entire domain, like a web browser and then others, so we can see the distribution is quite, they're mixed up with other domains. But if you just consider only Firefox, you can see here only Firefox, there is a clear-cut separation. It's towards one particular corner, and then the remaining executables are spanned across the chart. So this we understand that at executable level things are much more clear. And then so this is also we have recorded suppose a given program, we took a Google Chrome and then we tampered with it, and then we saw that we observed the performance counter data, so how the deviations are happening. So for certain performance counter data, so the deviations are quite prominent, like page file bytes, IO data, handle count, school page bytes. So the deviations after a certain time instant, so they are quite taking into effect. So this will help us to detect the tampering of programs. And then so this is what we are mentioning, the distance. So this is the cluster, intra-cluster distance of the Google Chrome, so various samples in the Google Chrome. So we have mentioned and drawn a box plot, and then we measure the distance of the tampered sample. So the tampered sample distance from the centroid of the untampered version, and then we can see that there is a uh, you know clear cut distinguishing factor. So this is far from the centroid, so that shows that even using uh, the microarchitectural events, the performance counter data, we can observe these particular differences. So we have used page file byte counters in this. So this is a conclusion. Like we target in our work only the Windows 10 operating system. However, the other operating systems are yet to be explored. We would like to extend our work to malware dataset. This is just a beginning with the benign programs, and we, in order to do that, we plan to integrate the perfect stack tool what we have developed to the Cuckoo sandbox, so that in a controlled environment we can detonate the malware. That's very essential because we are working in an industrial setting. And then we try to deploy much more advanced AI algorithms in order to characterize the behavior of the programs. And then we plan to increase our data set also. Now currently we have only 18 programs, but we plan to verify our efficiency of our proposed mechanisms or massive data sets. Okay, so thank you very much for your patient hearing.